In conditions of high altitude and/or high ambient temperature, the use of a water injection system can restore the thrust of a turbojet engine and boost the output of a turbopropeller engine. Typically, the water injection system is activated by moving the throttle to the takeoff position. We stated in the introductory lesson that the power output of a gas turbine engine depends upon the mass of air flowing through it and the acceleration imparted upon that mass of air. In conditions of high altitude and/or high ambient temperature, the density of the airflow through the engine, and therefore the mass of that airflow, decreases, causing a reduction of thrust in the case of a turbojet engine, or a reduction of shaft horsepower in the case of the turbopropeller engine. To restore, or as is sometimes the case, boost the power output of an engine, the airflow passing through that engine can be cooled by spraying water into it. The amount of water carried for use in these water injection systems can be large. The Boeing 707 and the DC-8 used to carry approximately 300 gallons of water injection fluid per engine, which had all to be used up during the 3-minute takeoff and climb. This equated to a water flow rate of 100 gallons per minute. The fuel flow through each engine at takeoff was 9,000 pounds per hour, or approximately 22 gallons per minute. This gave a water flow to fuel flow ratio of 4.5 to 1 through the engine during those periods when the water injection was being used. This diagram shows the maximum level of power available from a typical early design turbojet engine. The power from this engine is limited artificially by a component in the fuel control system of the engine. Just how this happens need not concern us here. Notice, though, that 100% of power continues to be available even up to 25 degrees Celsius, which is ISA plus 10. At ambient temperatures higher than this, though, the power available drops off. Now we can see the power restoration curve for the same engine after a water injection system has been utilized to restore the power available from the engine back to the 100% level. The ability of the power restoration system is, however, limited to only perhaps 25 degrees Celsius above ISA. The reason for limiting the thrust restoration of the turbojet engine to that of its flat-rated performance is that, although the mass of the airflow could be increased, with relatively few complications, by increasing the compressor speed, the maximum compressor outlet pressure has to be limited to prevent the engine compressor casing splitting under the excessive pressures that would be generated by using such a procedure. This diagram shows the power curve of a typical early design turbopropeller engine without a power augmentation system operating. Now the power output of the same engine has been boosted by 15% by a power augmentation system. Note that in this particular instance the power augmentation uses water methanol as opposed to pure water. More on this fluid later. In the case of a turbopropeller engine, if the water is injected into the combustion chamber, which is by far the most popular method of water injection, the mass flow through the turbine is increased relative to that flowing through the compressor. In the turbopropeller engine, this increase in the mass flow through the turbine is not used to increase the compressor RPM, and thereby increase compressor output pressure. Instead, the increase in mass flow through the turbine is absorbed by coarsening the pitch of the propeller to increase the mass of air being thrust rearwards, while maintaining the engine rotational speed at no more than the normal maximum. This procedure very effectively increases the shaft horsepower output of the engine. Some centrifugal compressor engines, and also some small American-designed axial flow compressor engines, used a system of injecting the water into the engine intake. Unfortunately, the water distribution was not of the best, and also the quantity of water injected had to be limited, so as not to cause an engine flameout. As we stated earlier, injection of water into the combustion chamber increases the mass flow through the turbine relative to that through the compressor. Because a comparatively lower level of energy is being extracted from the turbine, even though there is an increased mass flow through it, there is a related decrease in the amount of pressure and temperature dropped across the turbine. This means that there is an increase in the amount of energy available either at or after the turbine. This can be used to generate extra thrust, either by driving the propeller at a coarser pitch, in the case of a turbopropeller engine, or, in the case of a turbojet engine, by increasing the pressure at the propelling nozzle. A pure water injection system does have some drawbacks, not least because the water must all be used up on takeoff if it is not to freeze in the tanks as the aircraft climbs to altitude. It's logical to require an injection fluid that does not freeze. Thus, methanol is added to the water. The methanol serves primarily as an antifreeze. By injecting coolant into the combustion chamber, the turbine gas temperature is lowered dramatically. However, if nothing was done to counter this fact, it would lower the amount of power potentially available, because the turbojet is a heat engine, which relies on there being a large temperature drop across its turbine. The bonus obtained by using methanol is that, because it is an alcohol fuel, it burns, and thus adds to the temperature of the gases, raising the turbine gas temperature back to its original level. In order to regulate the amount of heat added, the quantity of water methanol injected into the engine must be carefully regulated. This is accomplished by a water methanol control system. The proportion of methanol added to the water must also be carefully controlled. A ratio of 40% methanol to 60% water by volume ensures that the turbine gas temperature limits should never be exceeded during use of the water methanol system. Thrust augmentation by afterburning, or as it's sometimes called reheat, makes use of the unburnt oxygen which remains in the engine exhaust gases to release more heat energy. This is achieved by injecting fuel somewhere between the turbine and the propelling nozzle and burning it. Afterburning is used to improve takeoff, climb and combat performance. Its use is mainly restricted to military aircraft. The one notable exception to this was Concorde, which was the only passenger-carrying aircraft using 4 high-ratio bypass turbojets with afterburners. Fuel is introduced into the jet pipe through discharge nozzles centrally disposed around the axis of flow. This enables some of the relatively cooler turbine discharge gas to flow along the jet pipe walls, which aids in cooling the jet pipe. This is required because the afterburner flame temperature may be in excess of 1700 degrees Celsius. An afterburning jet pipe is fitted with a variable area propelling nozzle. The area of the propelling nozzle is restricted during non-afterburning operation, and it's opened fully to allow for the increased volume of gas which is produced during afterburning operation. The selection of afterburner is usually initiated by the pilot moving the throttle lever through a detent or gate. Control of the nozzle is automatic. When the fuel from the afterburner is ignited, the pressure in the jet pipe, which is called P6 pressure, will increase. This causes a change in the pressure ratio across the turbine. The pressure before the turbine is commonly called P3 pressure, so the pressure ratio across the turbine is P3 to P6. The variable area propelling nozzle is automatically opened so as to restore the correct P3-P6 ratio. In the combustion chambers lesson, we stated that because the flame rate of kerosene is only approximately 30 feet per second, to prevent the flame in the chamber being extinguished immediately, we had to slow down the speed of the air entering the combustion chamber. In the combustion chamber we used components called the flare and swirl vanes to effect that reduction in velocity. Because of this low flame rate, we must also reduce the velocity of the gas stream through the afterburner, in order that the afterburner flame can remain stable. This is achieved by a diffuser, which is positioned before the afterburner section. When the afterburner is selected, an atomized fuel spray is introduced into the jet pipe through the burners. The atomized fuel spray is ignited by either an electric or catalytic igniter plug, or, in some systems, hot shot ignition. Once combustion is established, the gas temperature increases appreciably. The increase in thrust obtained due to the use of an afterburner depends entirely upon the ratio of the absolute jet pipe temperatures before and after the extra fuel is burnt. If, for instance, we assume a gas stream temperature of 900 degrees Kelvin prior to selection of afterburner, and the temperature of the gas stream rises to 1500 degrees Kelvin subsequent to its selection, then the temperature ratio is obtained by dividing 1500 by 900. This gives us a temperature ratio of 1.666. The velocity of the gas stream in the jet pipe increases as the square root of the temperature ratio. In our case, that is the square root of 1.666, or 1.29. This means that the gas stream velocity will have increased by 29%, and thus the increase in static thrust will also be 29%. As can be imagined, the fuel consumption goes up dramatically when the afterburner is selected, so its use is normally limited to short periods only. This concludes the lesson on thrust augmentation.